Hi, welcome to this week's design programming lecture. You've now covered variables, control structures, that is if and for, and as of this week, functions. And really, those are the three fundamental elements of programming. Congratulations, you made it to the end. Now we are going to cover a couple of more advanced topics over the course of the next couple of weeks. But there's really not that many. You've actually got all the building blocks of fundamental programming under your belt as of this week. All we're going to cover next is events, which is really just functions that get called by the computer under certain circumstances. And arrays, which are effectively variables where there's just lots of numbers in a list rather than one number or one string or whatever. And objects, which is really just a way to store a state and some functions that do something. So just a packaged up of some variables and some functions all in one convenient place so you can make lots of them. Those are really just ways to organize your code. But you've got all the things you need. Ways to store something, ways to choose something, and ways to package your code up so that you can do the same thing over and over again without having to write tons of code repeatedly. So now we're going to enter into the world of algorithms, which is, given those components, how do we organize them to do useful things? In this lecture, we're going to go through some of the really interesting algorithms out there that are possible given just those three elements, building from the simplest possible thing all the way up to some of the more advanced, state-of-the-art algorithms that can produce amazing results. The focus of this week is not on teaching you to implement these things in P5, although I do have P5 examples of some of these, but instead to start getting you thinking about how to get computers to do stuff. Because it might feel to you like you have learnt letters, but not words. You know A, B, C, and D, but you couldn't possibly put them together into something. Well, that's the difference between learning syntax, which is learning the things that a programming language can do, and learning algorithms, which is the way to do things with them. So we're going to dive into that world today. Some of you may ask, why should we learn what computers can do, the computer science of programming? Why should we learn what is possible in algorithms when we're interested in making art, when we're interested in being creative with these computers, when we're interested in being front-end developers or being able to prototype our design ideas? I would answer that the world of computing is never static, has never been static, and you should not, if you're interested in getting a career in this field, you should not prepare yourself to create what is out there today. You should prepare to create what is going to be out there in 5 years. Then, of course, you have no idea what that is. So you should learn about what is possible. You should take a minute and come with me into the admittedly technical, but also absolutely crazy world of what can be done with just combinations of those few simple components. And hopefully you'll be able to learn some of the amazing things that computers can do and then leverage some of those things back into your design practice. And what better place to start than one of the simplest algorithms that you get taught at the start of any computing degree? How do you sort numbers? This is a sorting algorithm. This is actually the bubble sort algorithm, which is basically the simplest and easiest to think of sorting algorithm that everybody comes up with when they first try and tackle this problem. Let's say you had a list of variables, a list of numbers that all started randomly arranged, and you really wanted to get them listed in ascending order. You can see this animation. This is actually straight out of the P5 references. You can see the link at the bottom there. How would you, as quickly as possible, organize that list? Well, you can see these moving. Numbers are quickly moving to the right and slowly moving to the left. Let's see if you can figure out what are the steps here. What's the underlying algorithm? To make it easier for you, I'll show you one that has fewer columns and moves slower. Here's the same algorithm moving faster. You see how it seems like tall ones flash over to the right, and then the short ones slowly propagate left. What might be happening here? What's the actual underlying function? The underlying thing, the instructions that you have to give to the code. You can't just say, hey computer, put them all in the right order. Actually you can, but that's because somebody else wrote this function. So here's what it's actually doing under the hood. And this is an animation straight from Wikipedia. It compares adjacent pairs of numbers and swaps them if the one on the left is higher. And it just slides along the list and it keeps doing that. So in this case, the high numbers propagate very quickly to the right-hand side. They automatically get moved to the end. In fact, you can guarantee every time you slide through the array that you end up with the highest number at the end, right? Because every time you go through, that highest number will get picked up eventually and carried through each of those pairs. You see this 8 got picked up as it slid past that 6 and then that 7, and now the 8 ends up on the right. You can say, lock that one off. Now let's go back. See, lock it off. We'll go back and we'll compare all of the other pairs, and we will end up with the second highest number sliding to the right. So each time you go through, you slide the next highest number across the right, and you do move everything else slowly, but eventually if you want to get those numbers that need to propagate further down, like in this case that 2, it'll take a bunch of iterations of this algorithm. So this you can now see is just a for loop that goes through and it says go from the first pair all the way to the last pair and swap them if they are if the highest one is on the left, and each time you go through the list, go through one less, so you don't have to go right to the end each time. Eventually, once you've gone through all of them, you can stop. This takes quite a while. Imagine if you had a list of like many thousands of things, and that's a whole field in itself. There is a whole thing out there called computational complexity, which is basically how long does stuff take to run, or more specifically, how much longer does it take if you add more input, because how long stuff takes to run just is how fast your computer is, but how much does the time grow as you add more data is where the really interesting question is. We're not going to get into that at all. If you want to learn about the wild and wonderful world of computational complexity, go take an algorithms course over at the School of Computer Science. They have some really good stuff, if that happens to be your jam. But all here, what we're learning is this idea that it's actually non-trivial to do some things on a computer. It actually takes a lot of work to figure some things out. That is a lot of work for the computer. It can take a lot of work for you and I as well to try and figure out how to make it go, but it takes a lot of steps. Just for the record, if you are interested in sorting stuff in P5, you can basically just do this. If you do have an array, there's this little variable here, mylist. We'll go over those in a week or so. You can just call mylist.sort and it'll figure it out for you. It's a little bit more complicated than these 2 lines of code, but this isn't about how do I make it work. This is about how does it work under the hood. What is the computer actually doing when I tell it to do this stuff? Here's another example that I love from the world of algorithms. If you've ever played a video game that had baddies in it, that had enemies, they have probably been following you around the screen at some point. And if you've played that game for any length of time, or if it happens to be a particularly old game, you've probably noticed that they're kind of dumb, that you can get them stuck behind walls or whatever. Well, that's the problem of pathfinding, which is a kind of search in space. This is an implementation of pretty much the standard, best known algorithm for pathfinding. It's called A*. We're not really going to get into too much about how it works, but you can see what's happening in this GIF, and I got this off Imgur, or possibly Imgur. I'm not going to dive into that particular debate, by the excellently named user Chameleon. This is trying to find its way from the bottom right to the top left, but it keeps running into obstacles. It's really computationally intense to search every possible path. So it branches out just as much as it has to, checking, hey, is this getting me closer? It needs some idea of what closer means, right? In this case, it's taking a guess based on the crow fly's distance, right? Is this getting me closer to where I need to go? Is this getting me closer to where I need to go? And in this case, it's pretty efficient. It's not wasting that much time on the colored squares before finding its eventual best path. So we want to study a little bit about what this actually looks like. How do you pathfind? What is a pathfinding algorithm? How do you search for something when you don't know the right way to go and there might be obstacles in the way? You can see this slowed down version. This is showing each step that it can take, but it can't just search every possible route because there's a huge number of possible routes even for this relatively small GIF. So it goes as close as it can. That is, it takes the direct route until it runs into an obstacle, and then it starts branching out and checking, oh, where could I go? Where could I go? Notice it has to check every possible direction because it doesn't know which one at this point is going to end up being better until it actually loops around the side of the obstacle and sees how it can get to that, how it can get closer to that endpoint. It really just has to go broad and explore everything it can, and then it can finally latch on to what's going to happen. This is the reason why enemies in a video game can sometimes get dumb, because they don't have enough CPU power attached to them to keep searching like this. They can sometimes get kind of stuck between things, or get stuck taking one step this way and then thinking they need to take one step this way and then one step this way, because they are not looking ahead far enough. They're being a bit too short-sighted, and they're picking up to a sort of locally good idea, but doesn't actually turn out to be the best optimal solution over time. These are algorithms. You can write out all the steps for what the A-star algorithm looks like. And other than the fact that it does use some of those arrays, which are really just variables that are lists, it doesn't use anything you haven't learned yet. It doesn't use anything but if statements, loops, variables, and functions. Here's another example of a fun algorithm. How do you pick the smallest set of points from among a set of points that lets you loop all the way around? You can see it's checking every other point to see if it can, which one is the leftmost, effectively, I think is the easiest way to explain it. So for each point on the outside, it has to check all of the other points. So you can imagine if there were millions of points, that would slow down quite a bit. Convex Hull is a relatively slow algorithm by those accounts. Why would you want to know what's the smallest set of points that can enclose a whole bunch of other points? Well, imagine you were doing collision detection, but with, instead of simple shapes like circles or something or other, with complex models or complex sprites, complex pictures. You wouldn't want to test whether every single part of your complex 3D model was intersecting with some other model. Let's do this in a way that it doesn't occlude the microphone. So you've got these two complex objects and you need to check whether they're intersecting with each other. It's much easier to draw a bounding box around them using this sort of simplifying method and say, okay, I'm just going to draw a hitbox, it's usually called, around these objects, and then see if the boxes bounce off each other, because I have to check much less. I have to check many fewer points for intersection as a result. Hugely fundamental to robot navigation, self-driving cars, video games, sort of fancy confetti style effects where things bounce off each other. Under the hood, something somewhere often calculates itself a convex hull. Is it going to be useful for you at any point? No, but it's interesting to think about how you would do this in various things. One last thing I want to talk a bit about is this idea of hill climbing, which is another kind of search. Imagine you didn't know where the best answer was, but you could move around in your space of guesses to see how well they perform. And the only way to check how well something can perform is by trying it out. And it's expensive to try it out. So you could say, oh, how does my design perform with red and green as the colors? Okay, now how does my design perform with red and orange in the colors? Red and a slightly lighter orange, red and a slightly lighter red, over and over again. And each time you have to go out and check with users or something along those lines. Assuming that there was an actual right answer, which in user testing there isn't, so maybe that's not the greatest example, you would eventually be able to draw a map of what kind of color combination makes people click on the next button as fast as possible. And that map might look something like this eventually, if you checked every single combination. But we don't have the time or money to check every single combination. So how do we search for something while doing as few comparisons as we can, while checking as few options as we can. The simplest way to do that is something called a hill climbing algorithm. So let's say you start in a random spot, just with a random combination, and you look at it and you follow these steps. So you check all of the adjacent squares on this grid. So check all the ones just in this local area. This, by the way, is called a local search algorithm because it does check everything around you. It just doesn't check every possible combination of colors. So in our color example, you'd check slightly lighter green, slightly darker green, slightly lighter red, slightly darker red, slightly hue shifted towards purple, etc., until you found what's the best performing one of those local examples. And then you switch to that. If you didn't move, you're done. You've found the best local answer. And now you go back and you do it again. All right, I'm going to check all the ones around here. I'm going to check all the things that are close by. And then I'm going to pick the best one of those. And then the best one adjacent to that, best one adjacent to that, and so on until you got to the point where all of the points around you are worse, or at least not better, than the one you're on currently. Then you can stop. This is the hill climbing algorithm. Assuming that you were blind and couldn't feel the slope of the hill underneath you, because, I mean, we'll talk a little bit about slopes of hills in a second, but assuming that you didn't have the capacity to just look and go, oh, that's the top of the hill, I'll go up there. Every time you check, you build a little bit more of a picture, a little bit more of a map of the space around you, and you keep going. This algorithm works fairly well. I mean, fairly well until you end up realizing that this is the actual map you're on, right? Because what happens when you start from there? You climb up that little hill on the left. You find a good solution. I mean, none of the solutions around it are better. But you didn't know that if you tried just off to the side there, you can't see that there is a much better solution, a much better combination that'll save money or that'll produce a better picture or whatever it is that you're trying to compare with your algorithm. So you never check that and you stop. Well, turns out one of the best changes to the algorithm that you can make is to just randomly try a whole bunch of times and take the best one. Because if you do this like 10 times and you start from each of these points, at least one of those is going up the big hill, right? There's no way to guarantee that that produces the best outcome, but it actually turns out that that's much smarter than trying to do a really good job or do something clever for your individual search. You just do a whole bunch of dumb searches, especially if you can do that on multiple computers at once, and then you'll come up with a pretty good answer. One slight modification to that is a search algorithm called simulated annealing, which sounds wild, but it's basically just about this idea that you could take crazy guesses first and then improve them over time. That is, get more conservative about improving them over time. But we're talking about some problem where there's some input variables, like how high do I want the robot to be, how long do I want the robot to be, how many wheels do I want the robot to have, and then those turn into how fast the robot moves or something like that. And you don't really know in advance what's a good configuration for your robot or for your plane's wings or for any other simulation, any other part that you want to learn, for the colors of your website, the engine diameter of your car, anything like that. You don't really know what's a good answer, and you don't have any directly measurable way of calculating what it is. So you need to do some simulations, do some intelligent guessing. It would be too expensive in terms of person power and in terms of computing power to calculate everything. So you just need to smartly guess a couple of times, pick the best thing you've got, and then stop. So imagine an algorithm that's pretty much like that previous one, except this time you check all the adjacent squares. In this case, we're looking at a one-dimensional problem. So you've got one variable that goes in and then one variable that comes out. Rather than the previous one where you had two input variables. You had your X and your Y input variables, and those convert into, I guess you could call it Z. The height is how good it is. In this one, you've got one input variable, just where you are along the bottom, and then that converts into one output variable, how good it is. Simulated annealing says, check the adjacent squares, in this case just left and right, and then only if a random number is less than this temperature variable, you move to the highest one. If it's not, move randomly. Wait, did I goof this? Yeah, temperature goes down So, yep, I totally goofed this. Give me 1 second. There we are. You saw nothing. If the random number is greater than temperature, then you move to the best of the adjacent squares. And so you can see this thing moves a little bit towards the local peak, but it doesn't tend to stay at local peaks because every time it updates, it checks against that temperature variable that you can see in the top left there. And if a random number is lower than temperature, it's going to just restart. It's going to move to a random place and start again. And then each step, you reduce the temperature slightly. And if the temperature has hit 0, you finish. Otherwise, you just keep going, right? So what you note here is that it moves very randomly at first. And then as the temperature starts to decrease, it makes fewer jumps and eventually gets stuck on the best one. There's slightly more to simulated annealing in that the jump is actually based on how good you are as well. But pretty much that's probably one of the best simulation algorithms when you don't know exactly how to find the best place and you kind of want to take an educated guess. You run this algorithm a whole bunch, slowly decreasing the temperature, and you come up with a pretty good answer. But what if you actually wanted to learn something about the hill? Remember, in all these search problems, we're not talking about a literal hill, because if you could see the hill, you just go to the top of the hill, right? But what if you could abuse, or rather leverage, the gradient of the hill that you were on? In all of these cases, we've just said, like, look locally, look left and right, look at what's around you, and then pick the best one. But on a real hill, you can feel the slope under your feet, and you can just choose to head uphill. So here's an example, and forgive me that I've flipped everything here, because we're now moving from the world of hill climbing to gradient descent. For some reason, we're now going from finding the highest thing to find the lowest thing, okay? It's just a slightly different branch of mathematics. Up is down, left is right, good is bad. Now this is a simulation of what's called gradient descent, which is a really important algorithm that's honestly not that much more complicated than the stuff that we were looking at before. In this case, all it says is calculate the slope just in the local area. Instead of looking at all of the nearby squares, now treat it as a continuous surface and just calculate the slope of that surface. P.S. That involves calculus. We're not going to go into exactly how that works. You probably remember from school that you did some calculus looking at slopes of lines. Well, you can also do that for slopes of arbitrary surfaces, and then you can look at all the different components of that slope, like this axis of the slope and this axis of the slope, and then you kind of average them together and find the best downhill. Do not worry, we are not going to go into that right now. Just think about it as feeling the slope underneath your feet. You can then just go down a bit. The way this is done in practice is that you have a step size, and then you take the local gradients, which is, you can see in the GIF here, you can see this little black arrows sticking out of the ball, and they grow longer when the slope is steeper. So you just take a step that is based on that gradient, so how steep is it, multiplied by some parameter that you have for setting the speed of the gradient descent. If it's really high, then it'll usually jump rapidly and go off in the wrong direction. So you take a small step and you go downhill a little bit. You recalculate and you go downhill a little bit more. And what you see in that simulation, it's something that looks a lot like gravity. Looks a lot like the natural process of a ball rolling downhill. And in fact, there's an expansion to this algorithm that just adds momentum. You know, the ball picks up speed as it goes downhill, which can be useful for kind of jumping over small little bumps. It can then go up over the bump and jump off over the side without losing all of its speed. But this is actually one of the fundamental components of all of modern AI. It turns out that this gradient descent algorithm is how Siri knows what you say. This is why every one of those fancy neural networks, every bit of deep learning that you've read about or seen on scary GIFs or whatever, each one of them, at the end of the day, used this process of gradient descent to find a good setting for the algorithm. to learn. Every time you say a machine learned how to tell cats from dogs, what it actually did is keep looking at cats and dogs and getting told the answer. And every time it got a bunch of stuff wrong, using this approach with very few modifications to adjust how it guesses and go again until it's good enough at telling cats from dogs. Or, to use a non-trivial example, telling normal moles from melanoma, a problem at which AI is now better than a doctor. It has more accuracy in recommending whether a mole should go and get a biopsy than a trained doctor. And if that doesn't tell you the power of this relatively simple algorithm written out in 4 steps that, other than figuring out the calculus bit and figuring out what the dimensions are, like how do I change my model to make a better guess at whether something is a melanoma. And if you're interested in that sort of stuff, then I've got a whole bunch of resources that I can unload on you for how to learn how image and computer vision-based machine learning works. But here in basic algorithm land, I want you to understand that all of the computational revolutions that you've lived through and that your parents have lived through, and again, dating my audience there, are fundamentally based on the same components that you've learned in the last 4 weeks: functions, variables, control structures. If you don't believe me, and they have the awesome power of simple control structures once they're put together into simple algorithms, I've got a couple of examples to finish off on. Simple search algorithms did this. This is a robot operating with no human control. It has learnt how to do this and is using its onboard cameras to better navigate this course. It learnt via gradient descent. It learnt via search. The dimensions, the variables that it learnt, were all the different ways that it can move all of its little motors and actuators. And the cost, how well it did, is whether it fell down. Now, I do have to tell you that they have very good simulators. They have supercomputers that have perfect physical models of this robot. This, by the way, is the Atlas robot by Boston Dynamics. You can see so much more awesome Boston Dynamics content on YouTube. Their Atlas robot can dance, backflip, jump up and down on boxes. It learns most of that. It does most of the initial learning inside a computer simulation. There is a simulated robot brain that is then only after it's learned how to jump off these boxes a whole bunch of times and done most of the expensive falling down bit in a machine. It's actually brought out and put onto the real boxes. It then learns more and fine-tunes more in the much more complex world of the real. But fundamentally, it is just variables, functions, and if statements combined with clever algorithms like searching via gradients that allow this computer to do this. Here's another example from the world of machine learning. None of these are real people. This is work by NVIDIA, the graphics card manufacturer, on an algorithm of theirs called StyleGAN. This one works a little bit differently. It's got a big database of real photos. Incidentally, those real photos in this particular example were all Hollywood celebrities, which is why you might notice a certain bias towards conventionally attractive, mostly white people in this particular data set. Since then, by the way, this field has moved on to using much more diverse and inclusive data sets, and I think it's done a great job of capturing human faces in all of their diversity. The way this one works is to compare the output, almost randomly generated output from an algorithm. It spits out a big bunch of pixels that make up an image, compare it to a real image, and have another algorithm try and guess which one's real. So get a real celebrity's face, and initially a just jumble of pixels in the right colors that come out of that algorithm, and you have a second algorithm that has to learn and say, that one's a face. And those two algorithms play a game with each other where they get better over time. The first algorithm uses gradient descent, that simple search function that we've been talking about, to produce better faces because it's trying to trick the second algorithm. And the second algorithm is getting better at not being tricked. It wins if it can prevent the generator algorithm from tricking it. And the generator wins if it can prevent the discriminator algorithm from telling which one is true. And over time, you end up with just using clever algorithms and a little bit of search, you end up with what are honestly really, really human-looking faces. This is from 2018. The field has gone even further since then, producing high-resolution, amazing photos. If you don't believe me, go to thispersondoesnotexist.com. So in each of these cases, it is functions made of control structures that operate on variables that can do all of these things, from sort of simple list of numbers to generate a realistic human face to get a robot to do backflips. You have the tips of your fingers the basics of the computing revolution. I'll see you in class.